Looks like we're live. Hello everyone and welcome to yet another Zozin session. How about that? I bet you didn't expect that shit to happen. Something with my nose today, I'm really sorry. So, yeah, today we continue developing a Porth programming language, stack-based programming language that we've been developing for like 3 weeks, I think. It's almost been a month since we started the development. So, and today we're going to continue developing this thing. So let's quickly make an announcement on Discord server. So this is going to be red circle live on Twitch. And what we're going to say today is that we're developing compiler in Python. Sarimun, hello, welcome. HTTPS twitch.tv/Zoding, and we're gonna ping everyone. Everyone is pinged. How about that? So you can find the source code of the compiler in here on GitHub, and also the playlist of all of the development episodes in here as well in the description. So if you're watching that live, you can find the source code of the project in here in the chat. Hello MSD Crafter, Carrot91, Droka, hello everyone, how are you guys doing? So today I think we're gonna have a last stream before we start doing self-hosting stuff, right? So we do plan to make our compiler self-hosted, but before we can do that, I need to develop a very important feature that will go a very long way during the development. So we see there's a problem that quite often I cannot keep track of all of the elements on the stack properly and their results. So again, the language is stack-based. Dabrik 2017, thank you so much for Twitch Prime. Thank you. I'm really sorry for all of the horrible sounds that I make. I think I'm a little bit sick right now, so I really apologize for that. So essentially, stack-based means that all of the operations are done by the stack, right? If you want to sum up two numbers, you have to first push these two numbers on the stack, and then you have to do plus, which will pop out this element from the stack, sum them up, and push the result back onto the stack. And after that, you'll be able to print that. So you can put any sort of numbers, for example, 34 or 35, right? So, and if you try to execute this program, it will print 69, right? So, and quite often we have different operations like write. Droka87, thank you so much for... Hello! Thank you so much for 6 months of Twitch Prime subscription. Thank you, and welcome to our Epic Porth Club. So, for instance, quite often we may have some operations like write. Another one, people are throwing money at me. So, hello Spegali, thank you so much for 4 months of tier 1 subscription. Thank you, really appreciate it. How are you guys doing? So, everyone is subscribing today, it's really interesting. Butterbroad TV, hello, welcome. So, we have operations like write, which can write some sort of a string, and after it wrote some sort of a string, it will return the result of the write operations. Since write is a syscall, and on Linux syscalls return the code, which indicates how the operation was performed. Was it successful or there was some sort of an error, right? So, and I constantly forget to either handle that code or drop it altogether. And because of that, I may have a bunch of errors where I do mathematical operations with the code without being aware that I need to drop it. So, and I had like systematically bugs because of that. So, and what I want you to do is to implement a simple static check. Essentially, I want a step that goes through the entire program and sort of meta-evaluates that program. Davawen, I hope I pronounce your nickname correctly, Davawen, thank you so much for gifting 2 tier 1 subs to Zoding community, and 2 people who got the sub. Welcome to the Zoding community. Do I need permission to fork the Porth repo? Every time I try in GitHub, it fails with "you cannot fork now." I didn't put any permissions. I didn't forbid anyone to fork the repo, so feel free to fork it. And I mean, what exactly do you want to do with the repo? Do you want to make a pull request? So if you just want to diverge the development, you can just, you know, make a copy of the repo. You don't have to use the inner fork functionality. You can just clone the repo, create your own repo, and just push it there. So you can do whatever you want as long as you follow the MIT license, right? So it's just, yeah. So you can even upload the source code on a different hosting platform and just keep it there. So yeah, so define. Okay. So essentially what I want you to implement, I want you to implement static type checking, not necessarily static type checking, but some sort of like a static step, so which will go through the entire program and meta evaluate this program. So essentially when it encounters 34, 35, it will push not the values of the numbers on the stack, but their types on the stack. So on the stack we're going to have int, and then it will encounter plus, and then it will look into the stack, and we'll see there's two numbers in there, all right? So and that will pop out these numbers and push another number as the result. So, and essentially if it will encounter that there is less than two numbers on the stack, this will fail the compilation, right? So this will straight up fail the compilation. And maybe to actually make it useful for the situations when I forget to handle the result of the syscall, maybe we're going to introduce different types. So the result of the syscall may have some different name, like code, right? So you have a code. And if you try to do plus, we can forbid any operations with the code and an integer, right? And we can make the compiler to tell you're trying to do arithmetic operations with the code. Did you really mean to do that? Or did you want to do something else, right? So, and if you still want to do arithmetic operation with the code, we may introduce some sort of like a typecasting, right? So you will cast a code into an integer, and that will help to catch some common errors, right? So, and we can also introduce types for booleans, right? So for instance, if you use something like this, right? If can only work with the booleans, and if you try to just put one in here, it will not compile properly. So we can actually do a lot of interesting things with this static type checking to actually help catch errors. And as I already mentioned, I think it will go a long way considering how many mistakes I've made because of the lack of this feature. So we'll see. So we've got a couple of new subscriptions. Thank you so much, Pakel1 for 3 months of Twitch Prime subscription, and Chirotical, thank you so much for 27 months of Tier 1 subscription. Thank you, thank you, thank you. So, all right. So let's go ahead and start developing this entire thing, I suppose. So we're going to implement something super simple. So there is one problem with this approach, and the problem is that we recently added support for command line arguments, right? So, and the way we implemented command line arguments is that we pushed all of them on the stack. Right, so essentially, if you take a look at the example that demonstrates how to use command line arguments, what we're doing here, we're just like keep popping them out of the stack, and yeah, so, and that introduces the problem. The problem is we don't know amount of command line arguments provided to the program at compile time. So we cannot easily sort of type check or stack check the command line arguments this way. And this creates like a very interesting problem that we need to resolve. And the way I see we can resolve that is to change the interface to command line arguments. So let's actually not push command line arguments on the stack, but rather provide two intrinsics, right? So literally the same thing that C does, right? So we can provide an intrinsic called ArcC, which will push the amount of the command line arguments, right? And we can provide ArcV, which pushes the pointer to the array of pointers to the corresponding strings, right? And every time you want to iterate through them, you will just push ArcV, and then you will keep dereferencing and so on and so forth, right? So, and that way, we never provide command line arguments via the stack. We provide them via these two intrinsics. So that way we can always, you know, properly check everything. So, and another interesting thing that we're gonna do, for instance, for the loops, we're going to do the same thing as WebAssembly. So in WebAssembly, there is a rule that you cannot underflow within the loop, and you cannot, you know, have additional elements at the end of the loop. So essentially, you can push as much as you want and pop as much as you want within the loop, but at the end of the loop, you have to have the same amount of elements as if you started. That way, you can just do one iteration of type checking and be sure that nothing is underflows or nothing is like overflows, right? So we're going to do a similar thing. And yet again, if you want to know more on the on how WebAssembly does the verification step, I can redirect you to this link. Right, it's a pretty good read on WebAssembly and generally how to type check, you know, stack-based languages. I'm going to put all of that in the description. WASM verification step, right? And for people who are watching online, I'm going to put that in the chat, which inspired the type checking of Porth. Right, there we go. Lindra Braga is gifting 5 tier 1 subs to the Tsoding community. Thank you so much. And everyone who got the subs, welcome to the Tsoding community. Thank you, thank you, thank you. So does anyone have any questions so far? Could we have error no as an intrinsic to store the return of syscall in the same sense of ArcC and ArcV? We could, but why? Why do we need to do that? Error no introduces a lot of problems, especially with multi-threading and stuff like that. So the thing about like error no and syscalls, libc, what libc literally does, it takes the return codes of syscalls and puts them in error no. You can just use the return codes of syscall and just like check them without any error no. Like you don't have to have error no to check for errors. Like you just don't. It's something that libc forces on you because of reasons. So free yourself from this box, right? And just do whatever you're supposed to do. Did I implement a mechanism to test command line arguments? Yes, I did implement a mechanism to test command line arguments, and now I store the inputs for the programs, for the test programs, in the same place where I store outputs. So I developed a very simple format that can hold input arguments, also standard input, and also the expected return code, the expected standard output, and the expected standard error. And the test script, test.py, actually uses all of that to properly test everything. So it reads this information, runs the program providing the command line arguments and the standard input, and then asserts that the program exited with this code, printed this on the standard output and this on the standard error. I haven't documented this format yet, but the reason why I'm using this custom format and not something like JSON is because I do plan to rewrite even test.py in Porth, so I need a very simple format that I can parse even in such a Spartan language as Porth, right? I want to have something super simple. And this format is actually super simple. I haven't documented it yet, but I do plan to document it in the future. So it's basically a sequence of fields, right? And each field, so there's only two types of fields. There is an integer field that stores an integer, and there's a blob field which stores the like arbitrary byte data, right? So, and yeah, So it's actually a pretty straightforward format. All right, and recently I introduced an example called name, right? So it's a classical program which basically asks your name and then says hello that name, right? It's a very simple program, and it's probably one of the programs that people write after they wrote hello world, right? So hello world just prints something on the screen, but name actually also reads something and prints something back, so it's a little bit more complicated than hello world. And let's actually take a look at how it works. So this is going to be Porth, and I'm going to actually compile this entire thing. So let's compile examples name.porth. There we go. So, and if you run name, what is your name? I'm going to print my name, Alexei, and it says hello, Alexei. So yeah, and yet again, this is a native program, right? Because we generated assembly for this program. So yeah, it's pretty cool. And to test this program, we do have standard input in the test case, right? So as you can see in the test case, we have Alexei. So the test.py will provide this input, and the expected output is going to be this, right? So yeah, we basically developed like a whole testing system for our language, which is actually pretty cool. Right, and there is a bunch of commands that allow you to update the standard input. For instance, you can do test.py, and you can say update input example name.porth, right? So I'm updating the input. So provide the std for the test case. Press Ctrl D when you're done. Okay, let's actually provide something like John, and I'm going to press Ctrl D, and it updated the test case, right? So it updated the input, but it didn't update the output. So if now I'll try to test this specific file, it will fail, right? It will say expected hello Alexei, but we found hello John. But at any point you can say update the outputs of this program as well, and it will reevaluate everything. And as you can see, expected one is going to be John as well. So this tool also makes it super easy to add new test cases, right? If you want to provide maybe like additional command line arguments, you can also do that. You can do update input, and you can provide a foo bar buzz, right? Then you provide Alexei, there we go. And if you revert this entire thing, there we go. We have command line arguments, we have standard input and stuff like that. So, and then I can update the output of this entire thing, and there we go. So, yep, that's pretty cool. So, and we implemented all of that from scratch. We didn't use any testing framework or anything like that. I just went ahead and implemented this entire system without using additional third-party dependencies, only Python and the standard library of Python. So it's pretty convenient. So yeah, isn't it cool? I think it's pretty cool. So let's remove that, and let's finally start working on the static type system, right? So static types. So the first thing we want to do, we want to probably introduce intrinsics for ArcC and ArcV, right? So this is what we want to do. Let's go ahead and quickly do that. Where is the list of intrinsics? So here are the intrinsics. So I'm going to introduce ArcC. It's going to be auto, and ArcV, and also going to be auto. So, and I'm going to just run the tests, just to trigger a bunch of stuff. And in here we have this thing. So for these intrinsics, we're going to have names. So ArcC is going to be like this, intrinsic ArcC and ArcV. So this is going to be ArcV. There we go. So maybe I'm not going to test everything. Maybe I'm going to test only one specific test, because as you can see, it just tests everything. So it produces a lot of output. So let's actually test very specific thing. Okay, so, and I forgot to update this thing. So it's going to be 33 now. So what's the next stuff? compilation of intrinsics. So how are we going to be compiling this kind of stuff? This one is going to be interesting. So maybe I'm going to actually start not with the compilation of intrinsics, but maybe interpretation. Right, so here is the interpretation of intrinsics. Right, so this is going to be 33. Let's go somewhere to syscalls, and there we go. If operand intrinsic argc. Right, assert false not implemented. Alright, if but Zozin, I hear you ask, there is an exception not implemented. You should use exception not implemented. And to that, my friend, I will say, no, I'm not gonna do what you tell me. There we go. That's my answer. Every time somebody tells me to use not implemented exception, I will put a new semicolon to my code. Every time somebody does that, you add a semicolon to the code. And no, I will not accept pull requests that remove these semicolons. These semicolons are essential for the code quality. ArcV, there we go. So this is going to be assert false not implemented. There we go. Don't forget the semicolon, of course. Alrighty. So, as we know, the thing is located on the stack, right? The thing is located on the stack. So, so this is where we push everything onto the stack, right? So at the end in here, so that means we need to place this entire thing like a sequence of pointers into the memory. This one is really freaking interesting, actually. It is really freaking interesting. So maybe I need to draw that. Maybe I need to draw that. Just a second. So let's draw the layout of the simulation memory. Right, let's take a look at it. My paint. Okay, go. So here is that, and here is the memory, right? So this is the memory. First byte is actually nothing. It is called null padding, right? So this is a null padding. So then we have a string buffer, right? We have a string buffer, and this is the place where we push all of the strings, the command line arguments. So the arguments go here. So this is the first argument, this is the second argument, and so on and so forth. And at the end, we have a little bit of space in here, and we push string literals here as well. So we store the command line arguments and string literals in the same sort of buffer. Right, so this is string buffer, str buffer. And after the string buffer comes the actual memory, the main memory that can be used by the program. So it's sort of like a heap. You can access whatever memory you want, like after this pointer. So here's an interesting thing. Where should we store the sequence of pointers to these things? We used to store them on the data stack, right? We used to store them on a data stack, but we don't do that anymore because otherwise we cannot type check all of that. So we need another buffer where we're going to store the stuff, right? So the sequence of pointers somehow. So maybe we need to allocate a little bit of memory there. Okay. So we have a null pointer padding, string capacity, and so maybe we're gonna have something like arg's capacity. And the question is how many bytes do we want to allocate for the arg's capacity? I suppose 640 kilobytes should be enough for everyone, right? So for all of these buffers, we're allocating like 640 kilobytes. All right, and here we're gonna have the following thing. So this is gonna be null pointer padding, string capacity, then args capacity, and then the memory capacity. So, and this is the whole memory address, right? So this is the whole memory address, and I think we need to more properly subdivide that, right? So I would like to have something like str PTR, right? And str PTR starts somewhere here, right? Then we can have args PTR, and it starts at, I suppose, this place, and then we can have mem PTR, which starts around like this, right? And these are the pointers that we can provide to the program. Makes sense? Makes sense. So essentially, I'm just like, you know, allocated like a huge chunk of memory, and I subdivide that chunk of memory like I would do in C. I think I already did that before, right? So I pre-allocated huge chunk of memory like with mmap, and I just subdivided for different buffers. I'm doing the same thing, but in Python for whatever reason. Just a second. Alrighty, so str size, and str size is rather strange, I would say. So str size, in my opinion, should be actually 0, right? And this is str offsets, but they're not str offsets. They're more of a like str pointers. So I'm gonna call this thing str buffer pointer, args buffer pointer, and memory buffer pointer, and these are gonna be str pointers. So this is a bunch of str pointers. So this is the opened file descriptors. By the way, we're kind of simulating Linux at this point. We have a table of file descriptors, right? Think about it. Table of file descriptors that map a number to a binary IO. And then if you have things like, I don't know, syscall 3, I think, right? And if you do syscall 3, we look up, so you provide FD via the arguments, we look up that FD and we read lines, like we write and the flush, and we're like literally simulating Linux kernel in Python. So... Of course, I don't really care about performance of this thing, because I do plan to rewrite all of that in Porth eventually. It's just like, I find it funny that we're just simulating Linux kernel in Python. People don't usually do that, but we do that because it's fun, actually. All right. Gia, what's up? Hi. We're simulating Linux kernel in Python. How about that? Here is the file descriptor table. We have memory and stuff like that. So we have syscalls, and yeah, it's pretty cool. Okay. So what else do we have in here? So string pointers, and so we push something on the stack. I don't think we have to push anything on the stack. So then we take the next argument. We encode this argument in UTF-8. Then we take the length of this entire thing and we put it into the memory. Just Lucy, thank you so much for 3 months of tier 1 subscription. Thank you, thank you, thank you, and welcome to our epic Linux kernel simulation club. That's what we're doing here. All right. So, and here we take the string size, I suppose, but this is not what should we do. I think what we should be doing here is str buffer pointer plus size, because this is where it starts. Another subscription from Deep Singularity. Thank you so much for 7 months of tier 1 subscription. Thank you, thank you, thank you, and welcome to our epic Porth Club. Hi, hi, hi. Hi, hi, hi to you as well. All right, so, and so we need some sort of like a str buffer end, I would say, and it will be equal to this kind of thing, right? So str buffer end, and this one is str buffer and plus n, and we put a value in there. And the interesting thing here is that at the end of this thing we also have to put a 0 because it's supposed to be null terminated, right? And after that we append the string size, rather like the pointer, right? The pointer to the stack. Dava when, thank you so much for tier 1 subscription. Thank you, and welcome to our epic Porth Club. Hope you enjoyed in here. Linux kernel in Porth when we rewrite Porth in itself, because when we rewrite it in itself, we're also going to have a simulation mode, so we'll also have to simulate the Linux kernel. Though it will be easier to not simulate the syscalls, because we'll be able to directly call syscalls during the simulation. So maybe we're not going to emulate the syscalls. We'll see. The winner gets T, that's for sure. So str buffer end, it's probably not str buffer end, it's more of a like argument ptr. So this is going to be argument ptr. Arg ptr, and here I was just pushing this thing onto the stack, and I don't think it is correct thing to do at all, right? So we need to push it into the args buffer, right? We need to push it into the args buffer, but we also need to know how many arguments in the args buffer we have. Right, so we need to have something like arg, something argc. VLC 242, thank you so much for tier 1 subscription, your first subscription by the way, and welcome to our epic Porth Club. Thank you so much, really appreciate it. So many subs today, it's really interesting. Porth Club, that's right. All right. So we keep track of argc, and it feels like, since this is argc, I think I should call this ArcV then, and the arg's capacity has to be ArcV capacity. There we go. Arg's capacity has to be ArcV capacity. So, and here what we're doing, we're appending this entire thing. Alright, so in the memory, I need to figure out where we have to do this stuff. So it's going to be arg v buffer pointer. So this is where the buffer pointer starts. Then we add argc multiplied by 8, because the size of the pointer is 8 bytes, 64 bits, right? And then I need to take a slice of this entire thing, plus 8, I suppose, right? So this is plus 8. And the thing I'm going to assign in here is essentially the pointer to the argument, but converted to bytes, right? So I need to do something like 2 bytes, and I'm converted that to 8 bytes in a little endian order, right? So this is going to be, how do you do that? I kind of forgot how you do that. So byte order, right? So you do byte order. There we go. So this is how we're going to be doing all of that. And I'm thinking, so maybe it would be nice to actually save that thing somewhere. So we could have something like argv pointer. Right, so this is argv pointer, and this is where it starts. Right. I'm doing an actual pointer arithmetics in Python. This is insane. Like, holy shit. Alright, so, and after that, after we edit this entire thing, I need to do argc plus 1 to increment the amount of arguments, right? So we used to push this kind of stuff on the stack, we don't have to do that anymore. Okay. Interestingly enough, so this is where we copy the string, and I think we need to increment the size of the string buffer in here and check that we didn't overflow. Right, and so we append the pointer to the args in here, and I think we also need to check that we didn't overflow the buffer by doing something like assert argc multiplied by 8 less or equal arg V capacity, right? So arg V buffer overflow, right? If something like this happens, we need the arg buffer overflow. All right, so that's pretty pog. So yeah, we iterated through all of the arguments, we added them into the string buffer, right? So they are now in a string buffer. And then we added the pointers to the string buffer to the ArcV buffer, right? So we're essentially preparing the memory and stuff like that. I'm literally writing a goddamn operating system in Python. Why am I doing that? It's actually super fun. I really enjoy doing that. So it's kind of fun. Not gonna lie. Maybe I'm gonna gain enough experience and then implement like a proper operating system, right? You know, people keep asking me, Zozin, where are you gonna implement an operating system? Well, I'm doing it right now in Python. So let's do the type check. I want to first type check the Porth and just to see if everything's okay. Probably not. Everything usually not okay. So it's taking some time because it's Python. But Zozin, Python is not slow. Look, Python is not slow. You're just using the wrong data structure. Zozin, Python is not slow. Whoa. Okay, so what do we have in here? Arg's capacity. So this thing is ArcV, right? And what's the next thing? String of sets. Okay. So I suppose we need to do something like str pointers, right? Str pointers. So, and if we find str pointers, if we find the current like IP, like instruction address in the table of str pointers, we put this thing in here, and we have to do this thing slightly differently, I suppose. So it has to be something like strptr, right? So it's strbuffptr plus str size, something like this, right? And this is where I'm gonna do that. So this is gonna be strptr, right? strptr. All right. So this is where the buffer starts, this is where the buffer ends, and this is where the new string will start, essentially. Then we associate this string pointer with the instruction pointer, and then we put the data at that specific place, right? We put that data at that specific place. And then we increment the string size by the size of the of this thing. And we'll also double check that we didn't overflow this entire stuff. And then we append the pointer that we just put into that table. Okay, everything looks okay so far. I really like that. Let's recompile everything, and everything's fine. I'm actually surprised that everything's fine in here. Nothing is particularly broken, and that's pretty sus, not gonna lie. That's pretty sus. So let's actually test some things, right? So I'm gonna try to do test pi. So I'm gonna run only one test, and it's gonna be a stack test, stack Porth, and something is broken. Okay, so this is because I haven't updated. Oh, okay, so it looks like the simulation has passed. Okay, so it only complains about compilation output. I'm really happy about that. It only complains about compilation. But the simulation went fine, I'd say. Nothing is particularly broken, which is good, right? Which is very, very good. Alrighty, so what do I want to test? I can just try to run Porth simulation tests, stack Porth, right? So this is a stack Porth and nothing is broken, everything looks okay. So привет мир, hello world, and yeah. So I suppose now we need to add support for the new intrinsics ArcC and ArcV to the compilation mod. So let's quickly do that. So I'm gonna go in here. So where? Here it is. L if op operand intrinsic argc. So for now, I'm going to say that this thing is not implemented. And then op operand intrinsic argv assert false not implemented. There we go. So, and let's just try to test the stack, and I forgot to update the amount of handled intrinsics, and so far so good. Okay, cool. Okay. So far we didn't really break anything in the tests that don't use command line arguments, right? So I think I'm ready to actually commit whatever we have. Introduce argc and argv intrinsics, but don't implement them yet, right? So we introduced them, but we didn't implement them. So, and now let's try to run the argv test and see how miserably it will fail. As you can see, in the simulation, it failed pretty miserably, right? So if we go here, it was trying to drop something from the stack, but there's nothing on the stack anymore, literally, right? So there's nothing on the stack. So we have to re-implement argv example completely, right? So how are we going to be implementing that? So let's actually separate this entire thing. And what I want to do, I want to push two things on the stack, the argv pointer and argc. Right, and while the amount of arguments is greater than 0, right, is greater than 0, I'm going to keep, updating this entire thing. All right, so let's take a look at what we have on the stack. We have argv and argc. So the first thing I want to do, probably, I want to copy argv on top of the stack so I can dereference it and see what's there, right? So this is what I want to do. So I'm going to do over. Over just copies the element over the stack. The next thing I want to do, I want to dereference that pointer, right? So there we go, I have a pointer in there. So once I dereference that pointer, I suppose I want to take its size, right? But if I take its size, I will lose it. So the first thing I want to do, I want to duplicate this pointer in here, and then I'm going to do strlen, right? So, and here I'm going to have strlen. So now I need to pipe these two elements on top of the stack into a write syscall. But write syscall expect these things in a different order. So the first thing I need to do, I need to swap them, right? So I swap them. So here we have a size of the buffer, then the buffer itself. Then we're going to push std out, right? And we're ready to call a write syscall, which will consume these three arguments, right, and return a return code, which I don't really care about, right, and I'm gonna drop it, right, so I'm literally dropping this entire thing. Cool. So after that, we also want to print the new line, right? So this is the easiest way to do that. We print a new line as a separate write syscall. And this is what we're left with at the end of the while loop. So the thing I want to do, I want to decrement argc and increment argv. So let's go ahead and do that. I'm going to do 1 minus that decrements argc. Then I want to swap these two things to get an access to argv, which I'm going to increment by 8 because the size of the pointer is 8 and we don't have the C-style pointer arithmetics, right? So we have to do it 8 times. So this is going to be plus 8 and that turns this entire thing to plus 8. There we go. And now we have to swap it back to get to the initial state of the loop. And there we go. So we finished the first one iteration of this loop. And it's gonna keep repeating until argc becomes 0 and then it will just quit. So this is the new way of handling command line arguments. This is how it's supposed to work. Did I make any mistake in here? I didn't think so. So I would say that these two loops are kind of similar. This one is a little bit more complicated, but it enables the static type checking because we don't have infinite amount of elements on the stack, right? Or at least a known amount of elements, if you know what I'm talking about. All right, so I'm not going to remove this implementation. I'm going to just comment it out. Though we're using version control system, so we're not losing anything. So this is the new implementation. Alrighty. So let's see if it will work. It probably won't work because we stopped ArcV and ArcC intrinsics with like to do. So let's just see if it's gonna fail. ArcV, and it, yeah, there we go. So it literally says not implemented. Okay, so for the ArcV, right, the first thing we do here, we're pushing ArcV. Oh boy, so let me see, it's gonna be stack, append, and what we're appending in here, I suppose, is going to be ArcV, ArcV pointer, right? So there we go, I think we implemented this thing, right? So this is the ArcV pointer, right? After that, and it hangs for whatever reason. That's very interesting. Why would it hang on a simulation? Because I would expect it fail at ArcC. Oh, I know why it fails. I know what it fails. Hangs, because I'm supposed to increment the instruction pointer. I completely forgot. So it was just executing the same instruction over and over again. So it's a common mistake that I do. And there we go. So the simulation now failed at ArcC, right? So it failed at ArcC. So in here we're gonna do append ArcC IP +1. There we go. So, and what do we have in here? So unexpected simulation shit. And as you can see, something went wrong. Something went horribly wrong. So we expected bar buzz for whatever reason. It's really strange. Why would we expect bar buzz? But that's what it is. But we got nothing. So none of these things actually printed anything, which is kind of sus, not gonna lie. Which is kind of sus. So we'll need to troubleshoot this the entire thing. So we're gonna do Porth by simulate tests ArcV Porth, and as you can see, it literally didn't print anything. It did print. Oh shit, this is interesting. So it printed only the argument in here, but if I do full bar, oh shit, did I actually made a fucky wucky and oopsie doopsie somewhere? Huh. Why does it say null in all of these places? So you know what I'm thinking? Can I just duplicate the strlen and print it just to see what's going on in here? And all of them are 0 for whatever reason. All of them are 0, and I don't really know why. I think I kind of know why. Is that because I actually placed them in a memory incorrectly somehow? Well, I do n+1 though. Interesting. So here is the argument. We take the length of the argument, right? So this is the string pointer plus size. So this is where it begins. Then I assign this thing. And at the end, I do 0, so I put 0 in there, and after that I increment the string, and I check that everything is okay in here. Okay, I don't see any problems in here. So ArcV buffer starts in here, ArcV pointer. So, and then this is the entire thing, and this is where I want to store the arg pointer, right? So this is where I want to store it. And we'll just put it in here. And then I do ArcC +1, and yeah, I don't see any problems in here, right? So there's no problems in here. This is really sus. So ArcC, right? So we put ArcC, and then we put ArcV pointer. Oh shit! I should have actually put ArcV buffer pointer. Oh my god. Yeah, okay. That's fine. Looks like... Oh, it feels like this variable, ArcV pointer, actually leaked through this loop. Right, if I define a variable here, it will be still available outside of the loop, right? that's a thing in Python, if I understand correctly. So let me actually double check. Right, so if I do something like I in the range of 10, and here I do x equals this, and then I print x, but I never actually defined x anywhere outside of the for loop, right? So yeah, so it's true. So basically, x actually leaks through this thing, and locals are apparently they're only locals for a particular function, which makes Python actually very good language. I think it's a very good language design, and it's definitely not error prone. Python is very good, well-designed language, and it's definitely not slow. Python is not slow, and it's a very well thought out language. I really, really like it, and I do not regret using Python for this programming language. Anyway, so let's continue. So everything looks okay. ArcV, let me take a look. So this is ArcV, so this is the pointer, and everything looks okay. So if now I try to execute this entire thing, and as you can see, it actually printed command line arguments. Would you look at that? That's pretty powerful. But it printed them in a really strange order, I would say. Right, I would expect them to print it in here. So that's kind of sus, not gonna lie. Okay, so let me take a look. So this is gonna be ArcV, and let's get rid of the dupe print, right? So I would expect this entire thing to be, oh yeah, because I explicitly reverted the pushing to the of the command line arguments, right? You see, it's reversed because I was pushing them on this data stack, but we don't have a data stack anymore, so this kind of reversing is not needed anymore, right? So now I can just do that, right? It's pretty cool. I can just do that. But one of the things we'll have to do, we'll have to skip the first argument, because depending on the simulation or compilation, this first argument is different, so it's kind of difficult to test this thing. So this is something that has to be changed in here. So I need to do, excuse me, ArcV 8+ and ArcC 1-, right? And that way, as you can see, we don't print the first argument, we just straight up skip it, which is fine. And now I think we fixed the simulation for the ArcV test. So this is going to be test py, and so this thing here is going to be tests ArcV Porth. So this is not how you do that, excuse me, so we just run it. Simulation went fine, simulation is fixed, and now we need to go and implement the compilation. All right. The question is, how are we going to implement the compilation of our nation? Because this entire stuff is located on the current stack, right? So it is located on the current stack, and probably we want to save the current pointer to the stack. All right, so let me see. So on the stack we do have ArcC, right? So we do have ArcC, and then we don't really have a pointer to pointer. So we have ArcV, so 0, right? ArcV1, ArcV2, and so on and so forth, right? ArcV1, V2, and yeah. So I suppose I can just save the pointer, the current pointer, to the stack, right? Somewhere to the memory, right? Just save it somewhere there. And then every time you have ArcC intrinsic, I'm gonna just dereference that pointer and give the content of this thing. Or if you do ArcV, I can just give you that pointer +8, which will point to the beginning in here. So essentially what I'm going to be doing, I'm going to be doing whatever C does, right? C basically gives you this pointer when you have ArcV. So that's the easiest way to implement that, I think. So yeah, and the current pointer to the stack is located in RSP, right? If I'm not mistaken. So essentially what I need to do at the beginning of the program, I just need to save the current RSP somewhere in the memory, right? So I just need to save it somewhere. Right. And everything should be fine, right? Everything should be fine. Alrighty. So essentially we're introducing the initialization of the program. You see, before we didn't even have any initialization after underscore start. We just like, this is the start of the program and we're starting compiling the instructions in Intrinsics. So now we need to have some sort of initialization, which is rather interesting. So our runtime becomes a little bit heavier, if you know what I'm talking about, right? It becomes a little bit heavier now. So let's take a look. So we probably need to reserve some space for the pointer to RSP. So where are we gonna put that? Okay. So this is the data segment. This is where we store the strings. And on top of that, I think I'm gonna just reserve thing for arguments. So I suppose this is gonna be args pointer. There we go. So this is the args pointer. And I need to reserve like 8 bytes or something. Though we don't really need to initialize that at compile time. So maybe I'm gonna reserve it at BSS. So it doesn't take any space in the actual executable, right? And the question is, what would be the best to do something like resq or maybe resb 8? I don't remember which instruction actually reserves 8 bytes. Does anyone remember? Okay, so nasm resb res D, I like literally don't remember because like a byte, how many bytes, resb, resword, and so on and so forth. I need 8 bytes. It's a resq. Okay, it's a resq, right? So we're gonna reserve 1 resq. That's what we're reserving. Resq. Alrighty. So and after that, we're gonna do what? Generate nasm, and I'm gonna move. So how am I gonna do that? So I suppose I need to just dereference this entire thing, right? Is that how we do that? Args pointer, RSP. Is that what I have to do? I think. I'm actually not sure. I'm actually not sure if this is how I have to do that. But anyway, so let's go ahead and do that. I might as well actually, you know, do GDB and see if it actually did anything. So let's compile. Let's do something like foo. Let's remove foo.py. Foo porth, and I think I'm gonna just have an empty program, I suppose, right? So it's gonna be easier to work with. Porth compile foo porth, right? So this is gonna be foo porth, and let's just go ahead and do this entire thing. And let's break on start and just to run. Layout awesome, right? Layout awesome. Oh boy, so we're moving this thing in here. Can I print args pointer? So can I cast it to maybe void star? So initially it is 0. So if I do something like next instruction, it didn't fail, and now we have a pointer to this entire thing. Okay, so if I take this thing and cast it to the pointer to the integer, right, and then dereference this entire thing and print, I should see 1, and there we go. So I did everything correctly. So and then I can do something like character, right, and add 8 to this thing to basically get the next pointer, right? And this thing will give me 27, which is some sort of escape thing. I'm not sure if I managed to do that correctly, to be fair, right? Yep, maybe I have to dereference. Nah, I shouldn't dereference it twice, but yeah, it's kind of close. It's kind of close to what I'm trying to achieve in here. Anyways, so yeah, we're pretty close. So this is the entire initialization of the runtime. We just save the current RSP to the args pointer, and that's pretty much it. Though, shit, fuck. The addresses in the memory, in the stack, they go towards the 0. I forgot to take that into account, right? So, and our program expects them to grow towards the positive side, right? It's kind of sad, isn't it? I think it's kind of sad. Thanks, Intel, very cool. Yeah, it's annoying. So one of the things we can do, we can just like reverse them in simulation as well, right? We can inverse them in simulation as well. But the question is how it's going to do on the other platforms, right? So on the other platforms, we'll also have to keep reversing that, and oh boy, it's really annoying. So I wonder if I can modify this shit on the stack, right? I should be able to, right? One of the things we can do, we can have a runtime that essentially inverses arguments, right? So here we can not only save the pointer, we can also inverse this entire thing. Though I guess it's fine. Let's actually just implement whatever we have right now and see how miserably it will fail, right? So outright, do something idiot. Thank you so much for tier 1 subscription, your first subscription by the way, and thank you, welcome. Welcome to our Porth Club. So here we're gonna do what? So this is gonna be ArcC, and then we're gonna do the following thing. So we're gonna actually move the value at arc's pointer to rex, and maybe I don't have to do that, but I still want to do that. And then we're gonna push rex onto the stack, right? And that will give us the thing. So let's give it a try. So this is a full Porth. I want to do args, and I'm going to just print this entire thing, right? So, and then this is going to be Porth and compile full Porth. There we go. So we don't have, it has to be ArcC. There we go. So we compile that, and let's just run this entire thing, and it completely failed. Cozy White Bear, thank you so much for 10 months of tier 1 subscription. Thank you. Thank you. Yeah. All right. So ArcC didn't work as I expected to work, which is kind of Saj, not gonna lie. Oh, this is because it's a pointer. Yes, that makes sense. That means I have to dereference it twice, I suppose. So I dereference the pointer to the pointer, so that means I have to do out right and then move rex. Is that something I can do in x86 64? I think I should be able to. Right, let's just dereference this thing twice, and that should work. All right, and there we go. We have one, which is nice. So, and if I provide more arguments like full, bar, buzz, it should be a little bit bigger. There we go. So as you can see, it works fine. So now the next thing we have to do is ArcV intrinsic. ArcV. Just thinking. So we can give the pointer to maybe, yeah, whatever. All right, so we have to do out right, move rex, args ptr, then n, out right, move. In this case, I think what I have to do is I need to subtract this thing, so I subtract rex by 8. Right. So that gives me a different pointer, right? It gives me the pointer to where the command line arguments start. And essentially here, I should be able to now push that pointer to the stack, right? So this is what we're doing in here. This is what we're doing in here. Okay. All right, so let's see what we can do. So yet again, it doesn't do anything special, and I'm gonna go to full Porth. Right, so in here, I suppose I wanna just do ArcV, right, and print ArcV just to see what's going on in here. So it gives me the pointer. Right, after that, I wanna try to dereference that pointer, and let's print that pointer as well. So that's a different pointer. All of them look like pointers. After that, I might want to try to take the length of that string, right? So let's take the length of the string. I'm going to include std Porth. I'm going to include std Porth, and here we have argv like this, right? And I'm going to do dupe, that will duplicate this entire thing, and then I'm going to do strlen, which will put strlen in here, right? So, and for now, let's just print this entire thing just to see if it gives like a reasonable number. As you can see, it printed 6, right? So essentially it printed 6. And if we take a look at the size of the string, it is 11 characters, which is kind of strange, isn't it? Like, where did we get 6 of them? Oh, no. So the 6 comes from here, right? Doesn't it? Uh-huh. Why do we have 6? When, in fact, here we have 5. This is truly sus. Where do we get the 6th one? So it cannot be 0 because we exclude the 0 from the calculations, right? We exclude the 0 from the calculations, so it is in fact kind of sus. Anyway, let's not print anything in here, and after that I want to swap this entire thing, so the size of this thing comes first, and then I'm going to do std out, and then just write, right? And then just write, and it printed bullshit. It printed complete fucking bullshit. In fact, in fact, it's kind of strange because it's like zeros and shit, you know? It's like zeros and shit. So I don't know. I don't even know what is going on. So we need to understand where in memory all of that shit is located. So maybe, no, I think I'm gonna make a small break. And after the small break, we're gonna try to figure out what is going on here and how we can fix this entire thing. Are you sure it's sub 8 instead of sub 16? The question is, why does it have to be sub 16? Because 8, we have 64-bit pointers and 64-bit, right? So if I go to something like, you know, 64-bit divided by 8 is 8, right? So if I understand everything correctly, right? So, and here is the pointer to the racks, and I have to subtract 8. Why does it have to be 16? I always used sub 16 to get the ArcV pointer. Maybe I'm wrong. It could be an interesting point. Maybe at the end there you have like a 0. So RSP might be actually pointing to the value before. So I need to know where exactly RSP is pointing. Let me see. x86, 64. Where RSP is pointing? Okay, so show me where it is pointing. Oh my god, can you just load a little bit faster? This is not very useful because it doesn't show exact address. Does it show to the value after? I have a strange feeling that here I'll have to do something like sub rex 8. Yeah, because yeah, look. The only reason why you would do -16 to get to the pointer ArcV is when you have right, so this is the stack, this is where it starts. You have ArcV and then you have ArcC. So here is ArcC and RSP points here, right? RSP points here, right? So you do -8 and you skip ArcC. So, and then you point to the ArcV, right? So you must be pointed to ArcV. Right. Should be +8. Yes, I'm an idiot. Thank you so much. Yes. Oh my god. Intel. Goddamn Intel. Why did you do that with the stack? Okay, I see. So everything's fine. Yeah, it's just I had to do a plus. I just had to do plus in here, and because of that, I don't even have to invert anything. Goddamn Intel, like, debated me yet again. Alright, so everything's fine, and if I try to do that, it kinda did nothing, but, I mean, whatever. So, yeah, so this is a move rex, and, yeah, so this is this thing, then I add this stuff, and let me take a look at this thing. Oh boy, and of course I didn't actually print it, that's why. So let's do std out right and drop this entire thing. So there we go, so now we have a foo. My god. Thank you, Intel, very cool. Alright, so, and because of that, I think the ArcV example should work correctly now. Alright, if I do something like tests, right, so it's going to be ArcV Porth, and as you can see, it's printing everything in a compilation mode. Finally, we spend an hour refactoring the way we handle command line arguments and introducing ArcC and ArcV intrinsics because of Intel. Thank you, Intel. Very cool. Okay, let's actually run the tests and see if everything's fine. All right, the test seems to be working. So yeah. So what's cool is that we don't even update input and output parameters. So the only thing we do, we just update the solution in here. Yeah. So let's go ahead and implement ArcC and ArcV intrinsics. Intrinsics. And I'm going to push that right into the repo. Okay. So, and I think now I want to make a small break. And after the small break, we're gonna go ahead and finally implement the static type checking, because now we don't have an infinite stack that the size of which is not known at compile time, right? So everything is known at compile time, and we can go ahead and sort of meta evaluate everything. But all of that is going to be after the small break.